Hey everyone, welcome to day 2 of distance learning. The purpose of today's video is to go through the lab for this particular chapter. The lab is up online, it's up on Moodle, including the PowerPoint for this chapter. So if you haven't done that yet, go ahead and download the lab. That way you can kind of follow along as best as you possibly can. I'm going to demonstrate it up on the board to give you the best idea that you possibly can of how to complete this. A couple of things really quick. When you're downloading this lab, pages 8 and 9 are the main sheets that you're going to have as far as going through the process of collecting your data. You'll want to print those out in a landscape form, not portrait. That way you have the length of the paper versus up and down. That way when you're performing the task, it gives you the most accurate data that you possibly can. So pages 8 and 9, the pages with the circles on those need to be in landscape format to give you your best shot of getting the most accurate data. So the content for this particular chapter talks about movement control and accuracy. We've talked about closed loop control and closed loop control systems that utilize feedback loops in order to maintain as accurate a movement as we possibly can. Remember, we did the star tracing where we utilize those feedback loops while we're producing movements in order for us to be as accurate as we possibly can. But we also talked about open loop systems with the evidence of these motor programs that allow us to be able to move really fast with the initiation of these motor programs, and those run through to completion without feedback while those are being delivered. But very rarely in the real world are we ever producing movements that are truly open loop or truly closed loop in nature. Usually there's some sort of combination of movement control and accuracy with speed that occurs when we're producing movement. Think about it from this standpoint. When you're threading a needle, when you begin that movement of threading a needle, you initiate a motor program of moving the thread closer to the needle, and you're moving pretty quickly. But as soon as you need to be accurate to get the thread through the eye of the needle, you slow down and start utilizing those feedback loops. It's no different than the majority of the movements that we produce, is that there's some sort of combination of both speed requirements and accuracy requirements. So we need both of those systems to be operating very effectively in order for us to be able to produce movements that allow us to be able to achieve some target skill or meet some objective in the environment. So this lab utilizes what's called Fitts Law. And Fitts Law states that there's a linear relationship between target size and target width that allows us to maintain both speed and accuracy. And this lab is meant to demonstrate that and introduce this concept of how fast can we move and still maintain accuracy. Now, everyone's a little bit different with this as far as individual differences go, but we can actually figure this out mathematically. There's a logarithmic equation on your lab that it discusses that pretty well. We're not going to go that in depth as far as figuring out exactly where you fit as far as from a mathematical standpoint on how quickly and how accurately you can move. But we could do that based on the data that we're going to collect, because what we're going to do is that we're going to collect data over the course of 18 trials. And then based on that, we could get the slope of the line. We could figure out exactly how quickly and how accurately you can move and how efficiently you utilize these open loop and closed loop systems in order to maintain both speed and accuracy. So a little bit of introduction. Here we go with the lab. So you will need someone to help you out with this lab, because someone's going to have to time you for these 20-second trials. Now, the purpose of this lab is to move between these two targets as quickly and as accurately as you possibly can. So the way that this is going to look is that you're going to start with your pencil in the left-hand circle, and you're going to move side to side as quickly as you possibly can. Now, you want to move fast, and you want to try to maintain accuracy. Now, that doesn't mean that you won't make mistakes, and we'll talk about the errors in a second, because we would expect that you would make some errors with this, and we want to kind of fall within the 3 to 7% range as far as maintaining that accuracy. So the important part of this is that over the course of these 20-second trials, you're going to be moving as quickly as you can between these two circles. So this is the way this is going to look. So we have it up on the board. We'll see if it pops up here really quick. So what you're going to do is that your partner is going to tell you to go, or whoever's timing you is going to tell you to go, and you'll start in the left-hand circle. And it's going to be the right-hand circle for you guys, just because of the fact that this is reversed for the video. And what you're going to do, as quickly as you possibly can, you're going to move back and forth between these circles as quickly as you possibly can for 20 seconds. Now, obviously, this is going to be a lot easier than your trials, because your circles are much smaller than what these are up on the board, but you're going to continue the trial for 20 seconds. Now remember, if you make a mistake and you go outside of the circles, that's perfectly fine, because we're trying to see what that balance is between speed and accuracy. So errors are okay, because again, when we talk about making errors, That's when we're talking about that switch between those open loop and those closed loop controls. So what's going to happen is that over the course of those 20 seconds, you're going to be moving as fast as you possibly can. Now, your partner is going to have to count for you, right? So you don't want to be counting because you don't want to be doing other cognitive processes while you're moving. So during those 20 seconds, your partner is going to count the number of taps that you make. Now, you're going to be moving pretty fast. So if you tried to count 1, 2, 3, 4, 5, 6, 7, 8, it's going to be really hard to do. So the easiest way to do this is to only count when you get back to the start. So count like this: 1, 2, 3, 4, 5, 6, and so on and so on. So what you'll see on your data sheet is the difference between what are called taps and counts. Now, counts are what you're going to be counting during your lab. So every time you get back to the starting circle, that's going to be your counts. Now, you'll obviously double that because you went from circle to circle. So your count is the number of counts that you make when you get back to the starting circle. Taps is the total number of taps. So you're going to multiply that by 2. All right? So other things that you can see on your data sheet is that you're going to see the number of misses, right? So the number of misses you're going to want to record as well. And then all you're going to be doing is you're going to be doing the number of taps divided by the number of misses, and that will give you your percentage. Now, you want to fall within about 3 to 7% accuracy as far as the number of misses that you have. If you're close, if you're at 2% or over at 8 or 9%, that's fine enough to count that trial for this particular lab. We're not doing this as much scientific as we possibly could. But if you don't have any errors or you find yourself in the 15, 16 or above range, you do want to probably redo that trial. So the purpose of this, again, is to move as fast as you possibly can. So you've got counts, you've got taps, you have your errors, all right? So all of that is what you have on there. Now, again, what we're going to be doing is that we also want to find out how long it takes you to move between those circles, and that's the data that we're going to collect. So you're going to take your 20 seconds divided by the number of taps that you get, and that's going to be how quickly you move between the circles, all right? So those are the values that you're going to have in your data collection: counts, taps, errors, and movement time, all right? So for each of the conditions, you're going to have 3 values for your movement time. Now, the information that you're going to be taking as far as your graphs, you have 2 different types of graphs. One is a scatter plot, one is a bar graph. Those are explained pretty well in the information that's provided in the lab. So take a look at that as far as how to create those graphs, the scatter plot and the bar graph. That'll just give you a visual representation of exactly what we're talking about with the speed and accuracy trade-off. Again, have fun with this. I know it's a little bit difficult when you guys aren't here and we can't kind of walk through this together, but it's explained pretty well in the lab. Hopefully this helps you out a little bit as far as giving you a demonstration of exactly what this looks like. But this is Fitts Law. It's how we utilize closed loop and open loop control systems in order to maintain both speed and accuracy. We'll go through the lecture on Friday to give a little bit more of a discussion and give you guys some more information as far as exactly what this looks like. If you have any questions, again, feel free to reach out to me. Shoot me an email. I will make sure and respond back to the entire class, because if you have a question, most likely other people in the class will as well. And again, with the climate that we're in, do the best that you can. Have fun with it. Collect your data. Use this as a means to and a tool just to give you an idea about the concepts. We'll go through the lecture on Friday, and then we'll move on from there. Again, we're going to move through this information fairly quickly. It's just a really quick, really easy, hands-on way to demonstrate the principles of movement control with speed and accuracy. Hope you guys have fun with it. I hope you guys are staying safe. I hope you guys are staying well. We'll talk to you soon. Bye.